maximum flow before the side view during flood. And by using this in different sections, we could approach for the best design or combination of groins and widening with a side view section. Another model about spillway capacity upgrade for Les Gloriette Dam in France. It's EDF project at Laboratory of Hydraulic Construction. And most of this work I have published in one journal paper. I can give you access for this. So the idea of this spillway, here is the existing spillway, and the capacity during flood is not efficient, or is not, during extreme flood is not so efficient, and the efficiency of evacuation, the flow is very low. Because of that, EDF, they are thinking or already constructed to construct a piano key weir. It's one weir in order to enhance the flow accessibility from the reservoir to the spillway. And in that time, we tried with several geometry of the piano key, or it looks like piano. It's almost one weir looks like piano, and in that case, we tested with large-scale particle image velocimetry in order to find how and what is the best location of this piano key in order to increase the flow capacity. Another physical model, it was for La Paz in Bolivia. This La Paz is situated in the western part of Bolivia between elevation 3,300 and 3,900 meters. The slope is very high, exceeds 20%, and we would like in this sanitary pipeline to define the new design with higher flow capacity, because they have lots of cavitation and erosion in the pipeline itself, and we could, by physical model, start to have different geometry for the steps or stair types, and of course with different geometry and different characteristics for flow, we could achieve that. In the beginning we have like nap flow, and after that skimming flow, and finally we could also test with and without roughness. And it really was very fantastic to find how we can reduce or evacuate maximum capacity with low velocity or dissipating more energy in this pipeline. Okay, so that was also. So one model is still in the Laboratory of Hydraulic Construction in Lausanne, and the TISTA model. This TISTA power plant, it was in India, one hydropower plant in India, and the power plant, it was one reservoir, and they would like to construct a runoff river power plant, and here the reservoir, and they construct some gated spillway with a stilling basin, large stilling basin, and then they have two power intakes going to the powerhouse. And in that model, we tried to, that was the original design by the Colenco company. And then we, at the laboratory, we tested this model, but finally we found that the efficiency of evacuating the flow and the sediment, because this stilling basin, the idea is to trap the sediment before reaching to the turbine, because it's very harmful. So we found this design of entering was not proper, so we have changed in the model what is the proper way to have more with clear water and without with sediment, also how we achieve or evaluate the gate operation acting to the bed level deviation. So, and here one result of large-scale particle velocity metric. Another problematic was the influence of the geometry of shallow reservoir and on flow and sealing deposition pattern. Here's these two pictures from Germany, I think, and these two reservoirs have different shape. And the idea how we can modify the shape in order to reduce the coming sediment. Of course, when the sediment is coming, it's deposited, and there are several strategies exist. Either we flush the sediment. This is a Bodendorf reservoir in Astoria, and we can see by flushing this sediment, we can reduce the deposition which already exists in the reservoir. But there are several techniques and strategies to do that, and one of these techniques we tried to play with the geometry. Or this is of course small and shallow reservoirs. But however, in the laboratory, I constructed one model. So we have here a mixing tank and water. So this is the mixing, I put the sediment, and then we have like mixer. Okay, this is the mixer, and here is the flow with sediment is coming to the inlet pipe, and then going to the reservoir, which has 6 meter per meter, and from the outlet with a flap gate, and here's some stilling basin to collect the sediment at the end. And this is a general overview of the model. But what was the objective? As I said, we would like to find the optimal geometry to reduce the sedimentation in the reservoir. So we started with a clear phase model, and here's the model. You can see these particles I distributed as a PVC particles in order to have a surface flow, and this is a surface flow pattern, and we can see clearly that the jet is entering straightforward, and then it deviates to the right side, creating a large coherent or eddy, and this eddy was associated with another two small eddies. But we could do another investigation before that. This is in the beginning, in the stagnant water, and how the flow is evolving, and why this jet were deviated to the right side. And we could find that in the beginning we have a normal straight flow, and these two small circulation or eddies start to initiate and become more larger, and then one of these, because of different pressure between two sides, one of these small eddies getting bigger and push the coming jet to be deviated to the right side. Okay, so here another phase we have with the sediment, and we can see how the flow. In the beginning it was straightforward, but then it was deviated flow, and then large circulation. But after putting sediment, this behavior has been modified and become completely straightforward, and we have a large deposition in the center line with two large circulation cells on both sides. So it was really very interesting. I have several setups, as you can see here. The reference geometry is a rectangular one, and then we reduce the systematic way because my supervisor is Swiss German, so we working always like systematic. So we have a reduced basal width, reduced basal length, and then we have some expansion angles. Of course, there are lots of things to be discussed for that one, and we have here 5 minutes. So we have here some numerical simulation with, it was a cooperation with HAC in Belgium, Professor Michel Breton. And this another 3D simulation were done in Japan by me and another professor in Kyoto University, and really we could simulate that with 2D and with 3D very. It's not easy, but it was somehow only the reference geometry. We couldn't make for other geometry. So this work in Japan, Kyoto University, we would like to have the concept of dry dams. Dry dams means these dams working for flash floods, and these dams, as you can see, working almost dry the whole in the whole year, working or functioning only during flood. And the objective of dry dam, so no gate, and where there is no gate, so the flow and sediment is very easy to access outside to the downstream. So the idea is this stilling basin, somehow the current design, they have like end cell. So this end cell is blocking fish and sediment to be passing to the downstream. So we would like to enhance the geometry, how to design this stilling basin geometry, a change in, we have a new concept to have it in ground stilling basin, very deep and naturally will be devolved with sediment deposition, and there is no end cell, of course, and once the sediment deposited and filled with the sediment deposit in the basin, it will be evacuated to the downstream reach. And we have like several objectives for that, and here are some parameters, and based on, of course, some model scale. And yeah, this is the idea. This is a model we built in the lab. We have the flow, and we have some gate here or dam, bottom outlet, and of course the sediment will be deposited, and naturally fish and sediment will be able to transport to downstream area. But we also thinking to construct some cylindrical tunnels in order to dissipate more energy